The fourth part of the course for the production of die casting dies, according to Nadca 207, will focus on heat treatment. Since each die insert has to go through the heat treatment process several times, it is a very important part of the tool-making process. As already mentioned, the main role in success is the choice of material and its properties. The task of heat treatment is to maintain these properties, but not to worsen them. But they cannot be improved in any case. The criterion for measuring success is again the impact strength of the material after hardening. How to maximize these values will be shown in the next part of the training. Nadca 207 provides this process flow for heat treatment. In reality, each insert should go through a heat treatment with additional heat operations. The usual procedure is as follows: drawing documentation of the insert, purchase of material, input testing of material with ideal oil quenching to verify steel material capability, roughing the shape, annealing to remove stress at a temperature of 600 to 650 Celsius, machining of the insert with additions for hardening, hardening and 2 or 3 temperings, material testing to verify impact strength after hardening, final machining of the insert including EDM, annealing after EDM at 500 to 550 Celsius, post-oxidation of the die surface to improve run-in properties. In case of shape correction, annealing after welding at 500 to 550 Celsius, annealing after sampling to remove thermal fatigue stress. Therefore, each insert for high-pressure die should go through the heat treatment plant up to 7 times. The first thermal operation is annealing to remove stress after roughing. This is annealing without recrystallization at a temperature below A1. Usually, it is a temperature of 600 to 650 degrees Celsius. The aim of this annealing is to release the internal stress after roughening the material and thus stabilize the shape of the insert before the quenching. After stress annealing and before quenching, fine machining must be included, with final additions for quenching. Annealing should take place in a vacuum furnace or under a protective atmosphere. If it is carried out in air, surface decarburization and oxidation along the grain boundaries must be taken into account. In this case, it is necessary to remove at least 1 millimeter from all surfaces of the insert. Some tool shops try to combine this stress-relieving operation with the process of quenching and tempering, without the under-operation machining. Such a procedure does not make sense, because the goal of this annealing, the reduction of distortions during quenching, will not be fulfilled. Because the stresses on the roughened insert are not visible, this operation is often ignored, and one relies on the fact that it will work out somehow, or that the result will have a negligible impact on the deformations. However, it is necessary to realize that after roughening, the tensile stress on the surface can be 200 to 500 megapascals. If we assume that 200 megapascals of stress is released during annealing, then the related dimensional change will be as follows. For characteristic dimension of 100 millimeters, 0.0952 millimeters, for 300 millimeters, 0.2857 millimeters, and for 500 millimeters, 0.4762 millimeters. The calculation is according to this formula. For large inserts, we can have a dimensional change of the order of about half a millimeter. That is not a small change. We therefore recommend a roughing allowance of 3 to 5 millimeters for the insert itself. After stress annealing, we then machine the insert shape to give a final allowance of 0.5 to 1 millimeter for quenching. If we apply this procedure and the insert shows deformations after hardening, we can be sure that these are really only deformations from quenching, without any deformations from machining. At the same time, this finishing machining before hardening will allow us to prepare the quality of the insert surface for quenching without significant stress concentrators. But this depends on the skill of the machine tool technologist. If we have doubts, the stress in the surface can be measured by X-ray diffraction, when we can calculate the magnitude of the stress from the shift of the diffraction lines. It can also be determined whether the stresses are tensile or compressive. An alternative method to the thermal process is vibration stress relieving. This method was developed for stress relief in large welded structures for which it is difficult to find the appropriate furnace size. The principle of the method is that the part of the insert on which we need to release the stress is placed on a rigid plate, and rubber silent blocks are placed on it. A vibration pulse generator is placed on the insert, which controls its frequency and is left to act for about 1 hour. Theoretically, this way, stress can also be released, without having to go to the heat treatment shop. Soft annealing is used very rarely in the Nadca 207 system. Normally, this is the condition of steel that is purchased with a maximum hardness of 235 Brinell. However, if the impact test after hardening is not okay, the heat treater must anneal the die to a soft condition, and just after that can repeat the hardening. It is an isothermal spheroidizing annealing process, the purpose of which is to restore the original perlitic structure by the transformation of tempered martensite after unsuccessful quenching and tempering. The usual annealing temperature for materials according to Nadca 207 is 840 to 870 Celsius. Since heat treater that perform vacuum hardening of die casting insert usually do not have a different type of furnace than vacuum furnaces, it is necessary to carry out the annealing process in a hardening furnace, taking into account the temperature. Soft annealing in air must be completely excluded. There would be irreversible damage to the structure of the material by decarburization and oxidation to a great depth. Another recommended annealing process is annealing after electroerosion. After this method of machining, a white remelted layer remains on the surface, which can be a source of cracks and is most certainly the reason for reduced impact strength and thermal fatigue resistance. This layer must be removed before using the die. This removal is only possible mechanically, for example by grinding, polishing, or blasting with a fine ballotine. The thickness of the white remelted layer is usually up to 10 microns. The total affected zone is then up to 100 microns. Annealing is without recrystallization, at a temperature of 500 to 550 Celsius. The highest permissible temperature is then 25 Celsius, below the highest temperature of the previous tempering. The holding time at temperature is usually at least 2 hours, and can be extended depending on the size of the die. Since at this stage the part is already almost finished, annealing must be strictly carried out in a vacuum furnace or under a protective atmosphere. EDM before hardening is not recommended. If it is necessary, then the layer needs to be treated as before, or even better. Instead of annealing to remove stress, include soft annealing or annealing with recrystallization above A3 temperature before hardening. Annealing after welding is another of the mandatory thermal processes. As with EDM, it is recommended to weld after hardening. In that case, the welded material has a chemical composition such that after welding and stress relieving, the same hardness as that of the insert itself is achieved. A miraging steel electrode is usually used. If welded before quenching, then the electrode has the same alloy elements as the die material, and will therefore exhibit identical quenching behavior. In all cases, however, it is necessary to always follow the recommendations of the steel manufacturer. The stress annealing is without recrystallization, at a temperature of 500 to 550 Celsius. The highest permissible temperature is then 25 Celsius, below the highest temperature of the previous tempering. If it is welded after quenching, annealing must be strictly carried out in a vacuum or under a protective atmosphere, because it interferes with the already finished insert. In some cases, laser welding is an advantage, but even in this case, die preheating is necessary according to Nadca's recommendations, for example 50 to 100 Celsius above the martensite start line. However, since the thermal radiation from the insert preheated to this temperature is so significant that it prevents the access of the welder, robotic mobile workstations are used for welding. In publication number 550, Nadca also deals with additive manufacturing technologies. Here he mentions that the DMD, direct metal deposition method, can also be used for die casting dies repairs, where a laser beam welds the gradually applied powder until the original shape is restored. Even in this case, stress annealing is mandatory. The last recommended annealing process is thermal fatigue stress relief annealing. At each cycle, a certain elastic stress is induced into the surface of the material until the plasticity of the material is exhausted. This stress accumulation leads to increased brittleness of the material and the formation of thermal fatigue cracks. The tension can be released by relaxation annealing, but it does not mean the complete elimination of the consequences of cyclic stress. It only delays the moment when the plasticity of the material will actually be exhausted. It therefore demonstrably increases the lifetime of the die. Annealing is without recrystallization. At a temperature of 500 to 550 Celsius, the highest permissible temperature is then 25 Celsius below the highest temperature of the previous tempering. The first annealing process should be included immediately after sampling, before the die is delivered to the customer. Since it is working in finished dies, it must be done in a vacuum or under a protective atmosphere. A similar effect is achieved with tools for extrusion of aluminium profiles by repeated nitriding, according to the Nitrex prescription. In some cases, the vibratory method can be applied instead of the thermal process. None of the annealing processes are mandatory, they are recommended only. However, their omission can lead to a reduced service lifetime of the tool. That is the best case. In the worst, the catastrophic cracks can occur, that mean the destruction of the entire die. It is therefore necessary to consider all risks well and always think about the resulting economic effect for the user. And now that we've gone through the annealing processes, we can start dealing with our own quenching and tempering. These are the operations that are decisive for the result. From the pictures you can see that the parts of the die casting dies have different shape, size, material. However, our aim is to ensure the same, as optimal as possible result of mechanical properties, especially impact strength in all cases. Deformations are secondary. First of all efforts are aimed at obtaining the corresponding optimal structure after hardening. Just as the purity of the material, the amount of primary carbides or the grain size has a major effect on the impact strength, there is also a correlation between the impact strength and the internal structure of the steel after quenching. It can be seen from the figure that, depending on the cooling rate, different structures can be achieved in the material. Each of these structures has different properties, including toughness. To maximize it, we must be sure that after quenching we have a martensitic structure, not bainitic or perlitic. Indirectly from this figure it follows that after quenching, we can achieve values of up to 20 to 27 joules of impact strength, as well as only 5 joules. An improperly conducted hardening process can therefore lead to almost a 5-fold deterioration of the material's mechanical properties. How the phase transformation in steel occurs is usually shown on the so-called CCT diagram. CCT is an abbreviation for continuous cooling transformation. At different cooling rates, the transformation curves of martensite, bainite, pearlite, carbides, and other phases in steel are analyzed. The user, especially the technologist, is able to determine from the diagram both the necessary temperatures for austenitization and the necessary cooling rate of the steel to achieve the desired structure. This diagram is therefore a basic document for technologists to determine the parameters of heat treatment. In the case of quenching of steels for hot work, according to Nadca 207, two things are important. Cooling should be fast enough to achieve a martensitic structure, see red curve, and fast enough to prevent precipitation of carbides along grain boundaries, see green curve. Only if these two conditions are met can we move the material towards the upper limit of impact toughness values. If we look at real structures, then we see that only by rapid cooling can we achieve maximum values of impact strength. But if we cool the die by crossing the carbide nose and the bainite line at the same time, then the structure will no longer have the toughness corresponding to the capability of the material, but will drop, for example, by half. The worst situation happens when we get to the pearlite area. This is already a situation that is completely unacceptable. The loss of toughness of the material will already be so great that we will only move to 20% steel capability. All work related to the die manufacturing process and selection of high-quality steel will be thwarted, regardless of economic losses. As can be seen from the metallographic samples, in terms of structures, they differ significantly from each other. But in terms of the resulting hardness, all structures are the same. They have the same 45 Rockwell. What does this mean? The tool shop simply does not know how the hardening actually turned out. It does not have the equipment and does not perform metallographic evaluation. For this reason, testing according to Nadca 207 is important. For the tool shop, it is usually the only way to verify the quality of the heat treatment. Otherwise, the fact that the structure was faulty after hardening will only be apparent to the customer by a part breaking or a low service life. However, this is usually too late, and the tool shop does not have much room to develop a complaint. Input data is usually missing. I mean information about the properties of the purchased material. Therefore, it is necessary to have a heat treater with a quality management system for heat treatment processes in accordance with Nadca 207, CQI 9, or ISO 20431, and at the same time regularly audit this heat treater. How to conduct this audit practically will be explained in another e-learning course. In order for the vacuum quenching furnace to work in the conformity to Nadca 207, it should be equipped with a temperature management and control system according to the American standard AMS 2750 in the latest version. Furnace instrumentation should be Type B. Although Nadca 207 does not say anything about detailed parameters, it is required that the temperature uniformity of the furnace be Class 2 ± 6 degrees Celsius. The entire temperature control chain must be in a calibrated state according to this standard. This means that TUS, Temperature Uniformity Survey, and SAT, System Accuracy Test, are valid on the furnace. Of course, the tool shop does not need to know anything about the furnace temperature control system. But if it audits the heat treatment plant, it should demand compliance with the periodicity of calibrations according to the standard. It is in toolmaker interest that the recorded temperatures correspond to reality. From the records, it should be seen at first glance that the programmed temperature of the furnace is in agreement with the actual temperature on the furnace control thermocouple. The furnace may not underheat, but neither overheat. The vacuum furnace must be leak controlled with a maximum leak rate of 6 Pascal liters per hour per AMS 2769 for vacuum heat treatment of steels. It must be ensured that no oxidation or carburization or decarburization of the surface of the parts occurs during the process. The furnace should be able to work with a nitrogen partial pressure of up to 2 millibars at temperatures above 800 degrees Celsius to eliminate the evaporation of alloying elements in the steel. To avoid slow cooling problems, Nadca 207 specifies a minimum cooling rate of 28 Celsius per minute, measured from the surface thermocouple Ts, and this rate needs to be maintained in the range from the austenitizing temperature to 540 degrees Celsius. The minimum nitrogen gas overpressure is not defined, but is expected that it will be from 2 to 10 bar absolutely. The vacuum furnace for Nadca 207 must be programmable and capable of working with a minimum of 2 batch thermocouples, one designated as Ts on the surface of the part, the other as TC in the center of the part. The furnace programming system must be able to control the isothermal hold and automatically adapt it according to the actual temperatures Ts and Tc. The furnace must be able to record data from the process in an understandable and readable form in the entire temperature. If we project all the requirements of Nadca into the theoretical record from the process, and we have the batch thermocouples correctly placed, then we get the graph of the process according to the picture. Because we have a sophisticated programming system, on the one hand, the temperature of the furnace is correctly controlled, and at the same time the data from Ts and Tc are evaluated so that the part is not damaged during heating, the part is properly austenitized, and it is ready for subsequent cooling. When heating, it is necessary to take into account that up to approximately 500 to 600 Celsius, the material is in a solid state and is subject to stress from the temperature difference between the surface and the core. It means between Ts and Tc. Therefore, even before reaching this temperature, it is necessary to check that the temperature difference is less than 110 Celsius. Otherwise, there is a risk that either permanent deformations will occur on the part, or it may even crack. Only above this temperature does the material become plastic, and stresses are reduced and dissipated. The control system of the furnace must therefore be able to react not only to changes in the temperature of the furnace, but also to exceeding the temperature difference Ts and Tc and slow down the heating to the permissible limit. In practice, this is usually solved by stopping the heating ramp and inserting an extraordinary hold in the heating period, when the furnace waits for the temperature difference Ts and Tc to decrease. The least problematic part of the heating is the area between the temperature of 650 Celsius and the austenitizing temperature. Nadca 207 says what the next preheating temperature should be, usually 800 to 850 Celsius. The prescribed temperature difference between Ts and Tc, less than 14 Celsius, is no longer due to deformations, but to ensure uniform heating of the die. The austenitizing temperature and time are also precisely defined in Nadca 207. From the point of view of the result, this is an important part of the process, which must not be too short, because the material would not be fully heated up, and the quenched structure would be significantly heterogeneous, and it must not be too long, because the austenite grain could become coarsened. In both cases with a negative impact on the impact strength values. Therefore, the following conditions apply to austenitizing. The soaking time at the austenitizing temperature should be a maximum of 30 minutes from the moment when the hardened part reached the austenitizing temperature at Ts, and at the same time the difference between Ts and Tc will be less than 14 Celsius, or a maximum of 90 minutes from the moment when the austenitizing temperature was reached by the first of the thermocouples, usually T-surface. Even if the entire heating process takes place under conditions that are not simple, a correctly modeled control system allows the entire process to be carried out completely automatically and without operator intervention. Moreover, completely independent of the size of the part. This is very important because it is the human factor that introduces errors into the system. Furnaces that do not allow temperature control from batch thermocouples should not work in the Nadca 207 system, and such furnaces should be clearly excluded from the system. Another very important part of the heat treatment cycle is cooling. In other words, quenching. The cooling mode needs to be split into 5 steps. Each of these steps has a different specification and also a different purpose. Now click on their description S1 to S5 for a detailed description. The pictures show a comparison of cooling cycles without isothermal hold, and with isothermal hold for a piece weighing more than 200 kilograms. The result is quite obvious. There will be a significant reduction in the temperature difference between the surface and the core, and thus a reduction in stresses. Without isothermal hold, this temperature difference is 300 Celsius. After switching on ISO hold, the temperature difference drops to 100 Celsius within 15 minutes, and ISO hold is automatically terminated. Cooling continues with the next step. Subsequently, the temperature difference will rise again to 180 Celsius, but we have to live with that. To prevent the insert from cracking at this stage, the designer must treat the shapes with the corresponding radii. The question is whether we can predict the necessity of an isothermal hold. There is a so-called buyout number, which is a criterion that tells whether a body is thick or thin from the point of view of heating. For thin bodies, we don't have to take into account the temperature difference. For thick bodies, we have to. The buyout number is calculated from the heat flow that supplies the heating system of the furnace, from the thermal conductivity of the material, and from the characteristic dimension of the part. If the buyout number is less than 0.25, it is a thin body. If it is more than 0.5, then it is a thick body. For example, the material Bowler W300, type H11, has a thermal conductivity of approximately 30 watt on meter and Kelvin. With an estimated furnace heat flow of 90 watts per square meter and Kelvin, and a material thermal conductivity of H11, the critical dimension is approximately 170 millimeters. For all parts with a smaller characteristic dimension, the isothermal hold is unnecessary and most likely will not occur. For parts with a characteristic dimension above 170 millimeters, an ISO hold is required and is likely to occur in automatic process control. The advantage is that if we have a sophisticated furnace control system and evaluate TS and TC, we do not have to solve this problem. So we can always use a program with 5 steps, and the control system of the furnace will decide whether the ISO hold occurs or not. The cooling capacity of the furnace is determined by the fan power, fan speed, heat exchanger size, gas velocity, and overpressure. Even with the best furnace design, every device has its limits in cooling rate. If the mold inserts are too large, the cooling rate of 28 Celsius per minute may not be achieved. Either we have to divide the shape into smaller inserts or look for a bigger, more powerful furnace. If it is still necessary to prepare a die with a large weight, then there is also a third option. Choose a different steel. As already said, in order to achieve a martensitic structure without the precipitation of carbides along the grain boundaries, we have to cool down the die very fast. Over time, new steel materials have been developed that have this parameter much more freely. It is primarily Dievar from Uddeholm, partly HP1 or TQ1 from Kind and Company. On this CCT diagram, we see the critical hardening points for H11 steel. The cooling rate is close to the limit of carbide precipitation and already partially penetrates the bainite. But we see a different picture on the CCT diagram for Dievar. The critical cooling rate shows that to exclude bainite from the structure, it is possible to cool almost 3 times slower than for material H11, and to exclude precipitation of carbides then almost 40 times. Even if DAVAR did not have ideal thermal fatigue resistance, it is already clear from these curves that the safety of hardening of dyes made of this material, in terms of the resulting structure, is much higher than that of the H11 material. This reduced risk can be used even if we do not have a vacuum quenching furnace with sufficient cooling speed or gas overpressure. In order for all this to work well in practice, the final program for quenching die casting dyes, if placed directly in the CCT diagram, must look like this. But we must keep in mind that the cooling rate is not specified by the gas overpressure in the furnace, but only and exclusively by the measurement from the batch thermocouples. This is crucial for the proper management of the process. It is important for the correct and automatic functioning of the heating and cooling process that the batch thermocouples TS and TC are correctly positioned. The type of thermocouples is not specified. They can be type K or N from 1.6 to 3 millimeters in diameter. A simpler situation is with the thermocouple TC, which measures the temperature of the center of the die. Usually, cooling channels or other auxiliary openings directed to the center of the part are used, but it must be ensured that in the case of a through hole, cooling gas does not flow through this hole. Glass wool, cibral, or similar heat-resistant material is used for sealing. It must also be ensured that there is no movement of the thermocouple during hardening. The surface thermocouple should be located in the center of the back side of the insert, roughly 1/4 of the width and 1/4 of the length from the edge of the insert. The thermocouple must be inserted to a depth of approximately 12 to 19 millimeters. It should be noted here that the heat treatment plant has no possibility of making these holes for thermocouples. It is therefore the duty of the tool shop and must be taken into account by the die designer as well. But he must know in which device the part will be hardened, and according to this furnace and heat treater usage, prepare a hole of the appropriate diameter. If we have no other option, we can help, for example, by placing the thermocouple TS in the screw, which we screw on into the thread on the die. There are many ways, but none can completely replace properly prepared holes from the designer. Nadca 207, from version 2024, now allows the use of an auxiliary steel block for measuring the temperature TC if we have no other option for placing the thermocouple. The size of this body is described as a sphere inserted into the largest cross-section of the insert. The thermocouple TC is placed in this auxiliary body, and it is assumed that it will have approximately the same temperature profile as the mold insert itself. The picture shows that in certain cases, this measuring body can have really large dimensions. At a minimum, this will affect the furnace's electricity consumption, because we are not only heating the mold insert itself, but also this auxiliary body. If we place only one mold insert in the furnace, we insert the TS and TC thermocouples according to the previous instructions. The position of the insert should be as shown in the figure. That is, in the furnace axis, so that the largest irradiated surface is parallel to the heating wall. The reason is the uniformity of heating of the body, when part of the heat is transferred convectively from the flowing gas, but part by radiation from the heating elements. In the case of installing multiple inserts, the situation is different. If we placed all the inserts as in the previous case, some of them would not be irradiated at all, because they would be shielded by inserts located near the heating. Therefore, the only possible solution is to place all the inserts perpendicular to the furnace axis. This will ensure that the inserts will be evenly separated, and their heating will therefore be similar. It is only necessary to remember the heating rate. In this case, the outer part of the inserts heat up significantly faster than the core, which is why permanent deformation may occur. The heating rate must therefore be limited to 220 degrees Celsius per hour at the thermocouple TC. At the same time, the furnace software must be able to evaluate the delta T between TS and TC, and if it is greater than 110 degrees Celsius, the heating must be stopped to reduce the temperature difference. Since each insert must be validated for cooling rate according to Nadca 207, the process must include a record of the thermocouple location, for example in the form of a photograph, as well as a record of the process parameters, especially TS. The read cooling rate is then stated in the processing report. If we are only quenching one insert, this is not a problem. However, if we are quenching several inserts in one batch, we must choose a solution. There are furnaces where up to 12 batch thermocouples can be used, and therefore a thermocouple can be placed in each insert. We only need to ensure that the individual thermocouples are identified in relation to the hardened inserts. We place TC in the largest of them and at the same time select the TS thermocouple in the furnace program, stored in the same insert as TC, intended for process control and delta T evaluation. However, if we have a furnace equipped with only 2 batch thermocouples and we want to harden several inserts simultaneously, we place both TS and TC thermocouples in the same largest insert in terms of heating. The individual inserts must have similar characteristic dimensions so that the smallest ones do not exceed the austenitization time set as a maximum of 90 minutes from reaching the required temperature at TS. From the point of view of cooling rate control, the record for the largest insert with placed thermocouples is then evaluated, and for the other, smaller inserts, it is assumed that it was faster than the recorded one. In vacuum heat treatment, it is common practice to create mix batches. Their appearance is diverse and cannot usually be predicted precisely because it involves the processing of completely individual pieces. In order for the heat treatment of these batches to take place according to the usual parameters, 2 basic criteria must be observed: approximate matching of dimensions and full matching of austenitizing temperature. Each steel has several processing regulations available. In the first level, these are regulations according to national standards such as the German DIN, British BS, or the American AISI. On the second level, it is the regulations of the steel manufacturers, usually narrowing the band of recommended austenitizing temperatures and other parameters. On the third level, there are regulations fixed to, for example, internal company standards, or in our case, to the Nadca 207 specification. Therefore, if it is processing according to Nadca 207, we must strictly follow the work instructions according to this specification and also the austenitizing temperature. Since only one temperature is given in Nadca 207, not a range, the processing must be only and exclusively according to this temperature. Therefore, if we want to heat-treat different steels in one batch, and these are parts for die-casting dies, we must harden together only those materials that have a common temperature according to Nadca 207. Once the cooling is complete, the die should begin to temper. The traditional view is that as soon as possible after quenching, but it is a question of what to imagine under the term as soon as possible. Is it after opening the quenching furnace door? Or is it after the martensitic transformation is complete? Or is it measured from the surface thermocouple TS after cooling the entire die to a surface temperature of 50 Celsius? As already stated, the quenching cycle is completed on a cooling station outside the furnace, in the open air. In some cases, a fan and forced air circulation are also used, but this is prohibited, for example, by the standard from General Motors. A piece is considered cooled when its temperature drops to 50 degrees Celsius. However, because we removed the insert from the furnace at core temperature of 100 degrees Celsius due to the risk of cracks, we have to wait until the insert cools down to the final temperature over the entire cross-section. In this step, we have to take into account not only the insert temperature, but above all, the definition of the martensitic transformation. Since the martensite finish line, which means the end of the transformation of austenite to martensite, is below 100 degrees Celsius, even if we remove the insert from the furnace when Tc is less than 100 degrees Celsius, this does not mean that the transformation of austenite to martensite is complete over the entire cross-section of the insert. Therefore, we have to wait. For large inserts, this can take several hours. This cooling period is critical in terms of internal stresses, because there is a large difference between the temperature in the core and the surface temperature, and the transformation of austenite to martensite occurs at the same time. The structure changes volume. As a result of this phenomenon, there is a superposition of stresses from the difference in temperatures and transformation stresses. And if it is in the area of tensile stresses, the strength limit of the material may be exceeded locally and the die may crack. Therefore, it is not recommended to speed up this phase of die's cooling. This waiting period for large inserts can take several hours. In order to avoid future discussions about proving of this delay between hardening and tempering cycles, this transition period must be defined and documented. But since the quenched parts are already out of the furnace, this stage of the process is not part of the quenching cycle record. Therefore, this situation must be documented in another form, by a photograph and a manual record on the production order with routing, or with entry to the thermometer book, testifying that the operator measured the surface temperature of the piece on the cooling station with a magnetically clamped thermometer, or in another way, and that the temperature reached, before placing it in tempering furnace, was really Ts equals 50 Celsius. However, it is already risky to cool the die below this temperature, as they could crack. Only when the inserts are properly cooled to surface temperature of 50 degrees Celsius, we can start tempering. The tempering process has two basic goals. Reduce the stress in the material by softening the martensite to the required hardness, and ensure the minimal content of the residual austenite, for the reason of stabilizing the structure and stabilizing the dimensions. The brittle martensitic structure is thus transformed into a tempered martensite with corresponding hardness and impact toughness. The recommended tempering temperatures are also adapted to this. For a properly conducted tempering cycle, it is necessary to be able to establish the core thermocouple Tc and thus measure the temperature of the piece. The tempering time is at least 2 hours and is calculated from the moment when Tc reaches a required temperature with the difference of, for example, 15 Celsius. The delta T parameter is up to the heat treater, but if he determines it, he must use it in the long-term time period to ensure the reproducibility of the results. The resulting hardness depends not only on temperature, but also on time, and a change in the delta T parameter means a significant impact on the tempering results. Tempering should be carried out under vacuum or under a protective atmosphere. The number of tempering is set at a minimum of 2 tempering cycles. In cases where we require maximum mechanical properties and dimensional stability at the same time, tempering 3 is recommended. The reason is as follows. After quenching, there may be more than 50% of residual austenite in the core of the insert, thus austenite where the transformation to martensite has not yet taken place. The remaining part is untempered martensite. After the first tempering, only the martensite formed during the quenching process is tempered. At the same time, with the continued transformation of residual austenite, new, not yet tempered martensite is formed. The structure would therefore consist of once tempered martensite, untempered martensite, and residual austenite. Only in the second tempering is the first part of the martensite tempered twice, the second only once. This may be sufficient for some applications, but where there is a requirement for maximum mechanical properties and dimensional stability, a third tempering must also be included, which ensures that the majority of the martensite will be tempered at least twice. The first tempering must be strictly carried out outside the secondary hardness area. In this area, due to precipitation of carbides, the material is brittle with low impact strength. Lower temperatures below 500 degrees Celsius are not suitable for hot work steels with regard to the working conditions of the mold and the temperature of the melt. For most materials, such as DeVar, H11, H13, or 1.2367, the minimum tempering temperature is 565 Celsius. Only for the QRO90 material, the first tempering must be performed at 600 Celsius. Exceptions are cases where we require the highest material hardness above 54 Rockwell, but this is not the case for die casting dies. The match at the first tempering temperature can be advantageously used for the economical hardening of mixed batches with parts made of the same or similar material with the same austenitizing temperature, processed to different hardnesses. After hardening, the batch is not split by material and by hardness, but is completely placed in a tempering furnace of the same dimensions as the hardening furnace to the first tempering temperature of 570 degrees Celsius. Only for the second tempering is the batch split into smaller batches according to material and hardness. Since the hardening cycle and each subsequent tempering can be carried out within 8 hours with some optimization of the batches, the entire process with 2 temperings can be completed within 24 hours. This is very important for tool shops. It also follows that for each hardening furnace there must be at least one vacuum tempering furnace of the same dimensions as the hardening furnace. Only after the batch has been divided for the second tempering can smaller furnaces be considered. After heat treatment, hardness is checked. Usually, the Rockwell method is used, corresponding to the prescribed hardness units on the drawing. However, the problem with classic hardness testers is the size of the table for clamping the part for hardness measurement, as well as the maximum weight of the measured piece. Therefore, other alternative methods are also used for hardness measurement in the form of portable hardness testers, measuring hardness based on ultrasound or reflection. However, these methods are not sufficiently accurate, if only because they measure hardness only in a thin surface layer of the hardened insert, which can be affected, for example, by local decarburization or other structural defects. Therefore, the most reliable method has proven to be the measurement of hardness with a portal hardness tester, with a Brinell measuring head with a load of 3,000 kilograms, and a tungsten carbide ball with a diameter of 10 millimeters. Due to the test load, the measurement is tied to a large volume of material under the indenter, and therefore this method best expresses the volumetric hardness. The resulting measurement values in Brinell are converted to values according to the Rockwell scale. In the next step, it is necessary to verify the quality of the heat treatment by impact tests according to the Nadca 207 specification. The figure shows how the test coupon is attached to the die for the hardening process. This coupon is separated from the die and sent for testing to a certified laboratory, for example, Element Materials Technology. The laboratory itself produces samples for impact tests and performs tests with the declared result. All this within 48 hours. If the impact test results are okay within the specification, the insert is released for the customer. The final step of the entire heat treatment process is issuing a certificate. The Nadca 207 specification does not say that the heat treatment supplier must also supply records from the cycles. The heat treater is only required to issue a heat treatment certificate on a form according to Nadca 207. This form contains everything necessary for the tool manufacturer and the user. Only in the event of future disputes over quality or damages will the cycle records play a role. In a standard situation, tool shops should not request this, because at this stage they do not need this data for their activities. Every heat treatment plant within its quality system is obliged to record and archive these records, usually for a period of 10 years. They are available during this time and can be returned to at any time in the event of a dispute. But the minimum period of archiving should be 2 years. This is the time when, according to the Civil Code, we are liable for hidden defects. As Nadca deals with the technical aspects of the die manufacturing process, there are also related corporate standards from General Motors powertrain or from the Ford Motor Company, which deal not only with the technical aspects, but also with the quality management system or business relations in the die manufacturing process chain for high-pressure die casting dies. These associated standards define approved suppliers for material, for heat treatment, and for material testing. For the GMP company, the entire process is managed by the die casting foundry, and for the Ford Motor Company by the tool shop. Therefore, in order for a supplier to become part of the system, they must pass a test period that usually lasts 30 months, and for a heat treatment supplier, according to GMP specification, 40 months. During this period, the supplier must fulfill the demanding criteria according to Nadca, with 95% reliability and higher. In the event of an error, the entire approval process resets and starts once again. Of course, this also entails financial risks. Just for fun, if the tool supplier delivers the die without the relevant documentation, he is not entitled to payment for it. If he supplies this documentation additionally, he is automatically penalized in the amount of $1,000. It can be seen from the above table that in some parameters, the related standards are even stricter than Nadca. For example, General Motors says that the hardening capability of the furnace must be at least 9 bar over pressure. Both the General Motors and Ford Motor Company standards then require 3 temperings instead of 2. The course of die's design and manufacturing is over. It includes my many years of experience and practice. However, the issues can be very complex and extensive, and may not exactly match your experience. If you have any comments or suggestions for improving the course, please send them to the contact listed. My goal is for the courses to provide essential information for heat treatment employees at all levels so that they can continuously improve. The level of content is therefore adapted to allow both existing employees and new employees who do not have knowledge in the field to take part in this course. Based on these comments, I will improve and expand the courses so that they are a real benefit to everyone. As you have probably noticed, the course was not voiced by me, but by the great speech generator 11 Labs. Thanks to him, my English will also be understandable. So thank you also to Bill and his voice for his contribution to the field of heat treatment. What you saw as a video on YouTube is just a picture of what is created in Adobe Captivate as an e-learning course. It is available on my website, jstconsultancy.cz. You can access it for €20 for 1 week, €40 for 1 month, or €60 for 1 year. The course is created in HTML5 format. However, it can also be exported to SCORM 1.2 format, which stands for Shareable Content Object Reference Model. Other formats are possible for different LMS systems. You can order this form at my email address, and you will receive the complete course in HTML5 code and a perpetual license for €200 per course. The compressed zip file will be 50 to 200 megabytes in size, depending on the content of the course. You can then install this file in your corporate cloud or in Moodle LMS 5.0, on SharePoint or in the HR module of your ERP system, such as SAP, which can communicate with a learning management system, LMS, that meets the LMS specification. In this case, you will be able to prepare a training plan for each employee, including an evaluation of its implementation and success rate. Each course contains a test with many questions, and the output is a certificate of successful completion of the course. You can archive these certificates and use them for employee motivational rewards. The advantages of e-learning are obvious. The employee does not have to go anywhere. They can complete the course anywhere, on a computer, tablet, or even a phone, at work, on vacation, or even at home. And you will be sure that they have the necessary knowledge to understand what is happening in the heat treatment operation. I do not know of any disadvantages, so I just hope that these courses will serve you and be useful to you. And what is my vision for the future? You can see this in this process map. So far, 16 have been created in Czech and English, and I will gradually add new ones, depending on their importance in the life of the heat treatment operation. I don't know if the courses are perfect, but I'm sure it's a promising form of education that we shouldn't ignore.